Hello, Len here. I'm going to talk now about how to get a better estimate of variance when you use a systematic design. This lecture is based on this paper here in Biometrics by Rachel Fuster et al. What's the issue here? Well, the variance estimates that we use for encounter rate variance, that's number of animals per unit line length, are based on the assumption that the lines were laid down at random. However, we know that in theory at least it's better to use a systematic design like this one here. What I mean by better is lower variance. So if you remember where the variance comes from conceptually, the variance comes from the idea that what would the variability be if we were to lay down multiple sets of lines onto this study area and repeat the study multiple times? How much would the number of animals that we detect then vary between the times that we did it? And if you use a systematic design like this one, then if animal density varies, for example, let's say there were more animals over in this corner, then each time you laid down the lines, you'd get some lines on that side and some lines on this side. So you'd catch some lines would have high density, some lines would have low density, but you'd always get roughly the same count because you'd always get lines spread over this whole area. On the other hand, if you use a completely random design, then if you have high density in one part of your study area, in some realizations when you lay down the lines, they might by chance all occur over at the other side and you'll get a low number of animals on every line. Or in other cases, they might all occur in the high density area and you'll get a high number of animals. So between the times that you went and did this survey, you'd get quite a lot of variability. And that's what the variance is trying to capture, the variance estimate is trying to capture. So we know that systematic designs will give you a lower variance because they spread the survey coverage out over the whole area, giving you a good picture of what's there. However, there's one thing about the actual variance being lower. There's another thing about estimating the variance, and there isn't an unbiased estimator for estimating variance from a single systematic sample. You can think of it this way. For a systematic sample, only the first line position is chosen, and then all the other ones are equally spaced or have some systematic spacing from there. So there's only one random number involved. Whereas for a random lines, each line is laid at random, so you have a random number for each line. So it's in some sense the sample size of lines, of independent lines, is only one for a systematic sampler. And there isn't a good way of estimating variance based on that effectively single sample. Even though we know the variance is lower than it would be, on average it'll be lower than for a random sample. So we have a bit of a quandary here. We know that systematic designs give the best variance, but they have the worst variance estimation. And in particular, we might overestimate the variance in general. So what we're going to do is we're going to use a trick that effectively uses stratification to improve the variance estimation for systematic designs. And that's what I'm going to talk about. Does this matter? Well, a lot of the time this doesn't matter at all. So a lot of the time, variance estimation based on random lines may produce a small overestimate, but it'll be perfectly adequate. And that's particularly the case when you have lines that are more or less the same length through the whole study area and animals that are more or less evenly distributed, like these ones here. So there's no strong pattern of high and low density areas there. This is the formula, the sort of standard formula that we use for estimating encounter rate variance. And in this kind of case, where the lines are relatively similar lengths and the animals are relatively evenly spread, then it will give a good estimate of the true variability, the true encounter rate variance. However, if there are strong trends either in line length or in animal density, then you might get an overestimate. And so this is a kind of worst case scenario here, where I have strong trends both in line length and in animal density. I have high density of animals on short lines and low density of animals on long lines. And this was sort of addressed in the paper that I referred to on the first slide, with a simulation that looked something like this. So you have a triangular study area and loads of animals and the short lines and few animals on the long lines, and you can see a systematic design. And in cases like that, the random variance estimator that I just showed you quite greatly overestimates the true variance. So in a simulation study, of course, you can lay down lots and lots of replicate lines over this area and see how much the encounter rate really varies. And that random variance estimator produced a strong overestimate. So what can we do about it? Well, we can use a trick called post-stratification. So the idea here is that we're going to come up with little strata that are just pairs of lines like this that are next to each other. I've got a case at the end here where there are 3 lines, whereas an odd number of lines, so I'm just going to pair the 3 of those together. So I'm going to group lines into small strata, 2 per stratum, or at most 3 at the end there. And the idea is that the trends in density within these strata are small. So there isn't a big density gradient between these two. And so using a random variance estimator within this stratum for encounter rate variance that assumes random lines is not going to be too far wrong. And so I'll use a random line variance estimator for this stratum and this one and this one and this one and this one. That's what this is here. This is the variance encounter rate within the strata. And then to get an overall estimate, I'm simply going to take an effort-weighted average of all these stratum estimates, and that'll give me an overall estimate of the overall variance. So that's what we've got here. So pooling them by weighting by effort. Now, one thing that you might think straight away is, didn't we earlier say that you need a reasonable sample of lines to get a good estimate of encounter rate variance within your stratum? And that's still true. So each of those estimates of variance from each of those little strata is not going to be very good. But because we're pooling together a lot of these little strata, then overall we should get a reasonably accurate estimate of the variance. How do you do this in distance? Well, in the variance tab of the model definition, there is an advanced button. And if you click on that advanced button, this window comes up. And the default is up here, is the design derived estimator. But what you do is click on post stratify, grouping the adjacent pairs of samplers. And what happens then is distance will group together the lines according to their ID. So line 1 and 2 will get grouped together, 3 and 4, 5 and 6, and if there's an odd number of lines, the last 3 will get grouped, and it will estimate variance separately in each one of those, and then it will pool them. So you have to have a systematic design for this to work, and you also need to put the adjacent lines need to have adjacent IDs for this to work, otherwise it's just going to produce nonsense. There's a further improvement, which is that we could use overlapping strata, so we don't just have to group together 1 and 2, 2 and 3, 3 and 4 and so on. We can also group together 2 and 3, so 1 and 2, 3 and 4, 5 and 6, sorry. We can also do 1 and 2, then 2 and 3, then 3 and 4, then 4 and 5, and so on. So you get these kind of overlapping set of strata. I'm using the same lines twice in some cases, in these overlapping cases, except for the beginning and the end. That's still okay because I'm just getting the average variance over all of these. It's just the way you do the averaging is slightly different. But it should produce a better estimate because now I'm averaging over more strata. I should get a more precise average. And so this is almost always a better option to choose. And so instead of choosing post-stratify grouping adjacent pairs of samplers, you choose this one, post-stratify with overlapping strata. And I would recommend always choosing this option rather than the one above. Okay, I was talking only about point transects up until now. So, sorry, line transects up until now. So what about point transects? Well, it is less of an issue for point transects because you don't have different line lengths. So the survey effort to every point is generally the same. It's generally 1. But if you do have strong density gradients and a systematic point transect design, which you should have, then you can similarly group into strata of 2 adjacent points or 3 adjacent points and do exactly the same thing. So if you number your points in such a way that adjacent ones have adjacent numbering, then you can just use the same method as before. But it tends to be a little harder to do, and you tend to have more triples if you sort of look on a map of your points. So you tend to aim for something like this. And in this case, to do something like that in distance, then you need to put in a little more effort. So what we do in distance is we're going to introduce a new field into the data. So here's my point transect data with an ID and a label and survey effort at the transect level. And what I'm going to do is I'm going to add a new field called var group. So I'm going to manually tell distance how to group them together. So I click on this button here, which will append a field, and I'm going to call it var group. It's of type integer. And then that adds the extra group. There it is. And then manually I'm going to type in group 1, group 2, group 3, group 4, group 5. So I'm telling distance which ones to group together. And then when I've created that extra data field, then in the model definition properties, I'm going to choose post stratify using the var group field in the sample layer that I've just created. And so that will do the post stratification sort of manually inside of distance rather than using this advanced button that I had before. And I need to say that the encounter rate is estimated at the stratum level, and for everything else use global. And the global density is the mean of the stratum level estimates weighted by effort. This doesn't let you do the overlapping version of the post stratification, but it does let you do the other version. And the advantage of this over letting distance do it is that you can manually choose the groups this way. Okay, so that's all I want to talk about with regard to systematic variance estimation.